Welcome everyone to Semifore's workshop, Harmonizing Hardware and Software, inside the engineer's head. We'll be exploring the challenges and best practices for building the hardware-software interface, or HSI, with some very interesting industry veterans. Please stick around as you'll be able to speak with them directly after the presentation and pose any questions you may have that come up during our discussions. So let's get started. My first guest is Dave Burgoon, Principal Design Verification Engineer at Microsoft Corporation. So Dave, welcome to this conversation about complexity in register design for RTL and chip development. Can you tell me about the complexity of the designs you've worked on, whether it's registers and gate counts, number of processors, hardware, accelerators, or any other factors that make the development of registers and utilizing registers in designs complicated?
Yeah, I can. We do lots of different types of designs, but one of the more interesting ones that I can talk about, which was talked about by Microsoft's Nick Baker at Hot Chips 2016, is our so-called holographic processing unit chip, HPU. It's part of the HoloLens product. This guy has 65 million gates approximately. It's got like 8 megabytes of onboard SRAM, gigabyte of DDR3 DRAM. It's a custom coprocessor, I guess you'd have to call it. It's got 12 compute nodes inside of it. Each of these nodes has two 10 silica extensa DSP cores with our own custom so-called tie instructions. It's got DMA engines associated with these cores, and also some custom fixed accelerator type IP, depending on what the compute node is destined for. So if you look at all the files that are basically the output of CSR compiler, there's like 608 of them. So if you were to try to just pretend we don't have CSR spec and CSR compiler, if you were to try to maintain those 608 files and have them be coherent, that's hard. Basically, we've got in the chip, there's like 335,000 control status registers, nearly 900,000 fields. The Verilog that comes out of CSR compiler, the Verilog RTL, there's over 585,000 lines of that, and it basically represents 5% of the total die area of this HPU chip. So that's an example of, I would call, a non-trivial chip that is using the product and the technique.
What is it? Would anybody know what that chip is used on? Or
Yeah, I said before. Yeah, I said before it's part of HoloLens.
What is HoloLens?
HoloLens is a mixed reality device mostly for the professional and scientific and commercial markets. We're actually on generation 2 of HoloLens, but the chip I'm talking about is the first one into the first HoloLens. Needless to say, we continue to develop chips for that product line and other product lines. But.
Oh, awesome. Thank you. So how does Microsoft coordinate the development of the hardware and software to make sure that they stay in sync? We know that can be a struggle, especially when hardware people and software people aren't sitting next to each other in development teams. They could be across the world. They could be across town or other buildings. How does Microsoft coordinate that?
Well, as far as address maps and control and status registers therein, a C-style header file, so-called .h file, is one of the key points of interface with the software team. And there's then also documentation. Typically use the HTML output. And we have a an in-house sort of flow or layer of automation on top of CSR compilers such that these outputs are, for practical reasons, checked into our version control system, and then the software team has access to that version control system, and so they can pull the latest, header files, et cetera, documentation as they see fit.
So do you check in all the outputs of the CSR compiler, or do you check in just what generates this and you generate it on the fly? How does that work?
Traditionally, I'm ashamed to say we have checked in the outputs, which is, in general, in my mind, a big no-no. But for practical reasons, like they didn't want to run CSR compiler or, have to go completely into our environment and run the automation layer that I talked about. By the way, plug, that was, I described that further a few years ago at DAC 2017 in a poster. So you can go find that if you want to know more about that. But so for practical reasons, we were using the version control system as a delivery mechanism. Now, actually, we are migrating away from that. We're moving toward adopting a product of Microsoft called Azure DevOps. And so I think the flows will change. And I think so-called pipelines in Azure DevOps will soon be running CSR compiler and producing so-called artifacts that the software team can pick up. So it'll be a different, sort of infrastructure and flow very soon. We're actually working on that as we speak. But classically, we just checked in the outputs to our version control system.
That gets to an interesting next question is, what are the best practices Microsoft have in coordinating these two disciplines? Obviously, with the switch to the new flow using Azure, what is it, Azure Azure Dev?
DevOps.
Azure DevOps. I'm assuming some of these best practices are going to be more implemented or changed. But what are some of the best practices Microsoft have in coordinating both the hardware teams and the software teams?
Yeah, unfortunately, for the sake of you guys, to me, the biggest challenge is, I guess you could say it's our problem, and that's at a program management level. So a classic problem is everybody knows that it takes a while to develop a chip, an ASIC or whatever. So the hardware people need to get started way sooner than the software people, right? The software people tend to be agile, right? They so that isn't ideal, because what ends up happening is the hardware team will come up with they will design the various address map hierarchies and their registers and fields as they see fit, biased toward what they need in the hardware. So a challenge is to get some representation, I guess I'll have to call it, from the software team earlier than we do now, so that they can, so that there can be more of a give and take between the hardware designers and the software team, reach some sort of compromise about what they'd really see. And, I don't want to overstate it in a negative way, but, in the worst case, they have to take what the hardware team came up with. But because by the time they're paying attention, it's kind of too late to make major changes on the hardware side. But to me, that had, the tooling helps with the mechanics of it, but coordinating the overall program so that the two teams are more synchronized, or we can get early feedback from the software team or something like that, is, it's an ongoing challenge. I would like to say we do better with each iteration, with each new chip, but you can appreciate there is a big disparity between, when the hardware team needs to get started and when you can get some attention and time from the software team early. So that's a big challenge.
You think the industry should go to that, where the software team has more representation at the architecture phase of a
Yeah, I
development?
mean, well, that's a sort of a philosophical question that, how optimal do you want everything to be? Um, like I said, the worst case is the software team takes what we give them on the hardware side, and they just have to live with it or adapt with it. But obviously, if you want to optimize both, it would be better to have some early give and take. Um, and don't get me wrong, when architectures on the hardware side are being put together, there is involvement. Obviously, you can't design a product like HoloLens by just thinking about the hardware. Uh, Especially, you have to decide which pieces are going to be done in software and in firmware and with dedicated hardware. So obviously, CSRs can be a part of that, but just on an architecture level, that's when we tend to get together earlier.
Is there any other best practices you could recommend? Anything else that you would want us to look into when we're trying to coordinate the hardware teams and the software teams? I know that there's been a lot of times in my history where the software team and the hardware team are antagonistic a bit, where they butt heads. So is there anything else that you could recommend on helping with that butting heads situation for teams?
Yeah, well, I keep going back to the original sort of non-technical issue of just how do you align these two programs, and you get people on both the hardware and software sides talking early enough so that there isn't a lot of rework later, either on the software or hardware side. To me, that's like a program management challenge, not so much a technical challenge. So what's my advice? To the extent that you can, get the teams talking together early, so that there are no surprises, or it's like, oh my gosh, the way this struct is laid out is completely at odds with the way I designed my software. And if you can try to minimize those numbers of those incompatibilities and those frictions, so much the better.
So, Dave, can you tell us a little bit about Microsoft's hardware software interface flow, or HSI flow, and how that works? I mean, you kind of alluded to that with the revision control as a mechanism to communicate to software, but how does the architecture team talk to the designers, talk to the software people? Do the architecture team design the HSI and then the RTL designers just get it? How does that all work?
Yeah, I'll be honest. I wish we had a better story there as regards CSRs, because we do have an architecture team that typically will write very abstract, System C or C++ models of the hardware. And, you just reminded me that that's also kind of another challenge, because they'll just, the architecture team might just say, well, okay, we have this parameter here and this parameter there. And they're not really thinking about the fact that someday these will end up as being control registers somewhere, or a lookup table somewhere in the address map. They're just part of an abstract model. So sometimes we do have a gulf between the models that the architecture team develops and kind of like mapping that to an actual implementation in terms of real memories and control and status registers. I suppose theoretically we should try to encourage the architecture team to use CSR spec and CSR compiler more upfront. But the challenge there is it's really just a very abstract model that in the most abstract case wouldn't be too concerned about the actual hardware implementation. So I suppose there's a bit of a manual process reconciling those models, which we do use in simulation and which the software team uses, reconciling those with the actual RTL level implementation of the various address maps and memories and control and status registers. So that's a challenge. And then the aforementioned challenge coordinating. There's really three teams there. The more we think about it, right? You have the architecture team, the hardware design team, and the software / firmware teams.
Question: is your architecture team on a chip level, or are they on a board level, or are they on a product level?
Yes.
All of them. Okay.
Yeah, I mean, but in the context of like an HPU chip, it's more blocks in the block diagram of the chip will be modeled, but then those models need to be mapped to actual hardware.
Is there any other challenges you'd like to share with regards to that Microsoft's facing in regards to the HSI?
Yeah, I guess what I was I'm going to repeat myself a little bit here, but hardware software interface. Well, okay. There's two types of software. There's modeling software from the architects, and then there's the actual production software. And I suppose you can try to lump those two together, but they are kind of two different teams. So anyway, coordinating all of those disciplines together can be a challenge. And yeah, I suppose, an ask I could have of a Semifore and CSR compiler is, right now the output for C or C++ tends to be very low level because that's kind of what the input is. But if there was some way you could have like system C register models pop out of CSR compiler, perhaps analogous to what you get with the UVM register abstraction layer output, that might be useful. Because the goal would be to have the architecture team who is working with the software team, who's working with the hardware implementation team. Early on, if we can have these abstract models and a single source, namely CSR spec, can somehow be involved earlier, that would be helpful. But right now, to be honest, the CSR spec is, in terms of level of abstraction, it's RTL, it's registers and fields, and its outputs are more consistent with implementation on the hardware side, not necessarily abstract modeling.
Dave, thank you so much for your time today. It's been great catching up. A lot of fun. One final question though: how can the EDA industry help Microsoft?
Well, there's so many facets to that question. I over the last, I'll say 10 years, I have been pleased that the infighting. I mean, I can remember the wars between VHDL and Verilog, and then we had the various verification methodology wars, but we settled on UVM. So, and I do like the role that Accelera has been playing in corralling, sort of mindless competition that left the end users fragmented. So I like all these standards, portable stimulus standard, UVM's a standard now, system Verilog's a standard. And so I guess one part of my answer is continue to do that. Continue to get together, embrace standards, compete on the merits of your implementation of those standards. Don't compete on the standards. But I think, especially over the last 10, 15 years, that's really the industry has been finally listening to the customer and coming together and compromising and adopting standards. So continue to do that. With standards, I'd like open APIs, more open and standard databases. Keep working on those standards. I think more of what you guys, particularly your CEO, Rich Weber, has been doing has been driving existing standards that Accelera governs, and to incorporate more and more features like in system RDL and IP exact and all that stuff. Keep doing that. That's all good stuff, because to the extent that we have choice as consumers of EDA around standards, everything gets better. So I don't know. It's kind of a simplistic answer. Keep doing what you're doing, EDA industry. Keep rallying around standards, and also putting forth new standards that address the most recent problems. Like, for example, the portable stimulus standard comes to mind. That's kind of a new thing, and it's a good thing. So,
Thanks, Dave. Now, let's welcome Jamsheed Agahi, verification expert and co-founder of Semifore. Jamsheed, you've spent a lot of time testing and verifying complex designs in your career. Can you share some of the best practices you found in dealing with this complexity?
Yeah, thank you, Josh. Looking back at my career, for the most part, I've had the good fortune of working alongside engineers who easily adopted methodologies that benefited all the teams involved in the design process. And one such methodology was adopting a single source hardware-software interface, whereby the design RTL designer, the verification team, and the software team would really be working off of the same single source. Now, back then, working at places like Silicon Graphics or other places where I worked and we designed complex systems, it was really impossible to accomplish the task without having such methodology. Now, you can think of, the RTL designer making a simple change to a register or a field, and the only way for him or her to let the verification or the software team know about the change was either to, verbally communicate that, or for the verification team to come back the following day and find out, yeah, the regression failed and something had changed. And that was really pretty much the way to find out. But the benefit of a single source methodology in defining the hardware-software interface was that now the RTL designer was able to make the changes to the interface, but it was self-documenting. And the verification team or the software team would immediately become aware of the change. And lastly, I can point to the fact that it allowed for automatic generation of some of the outputs that these teams were interested in, right? For example, if we think of the software team, and they're interested in header files. So that was an opportunity to be able to generate the software header files for the software team. Automatic generation of some of these files meant that we were able to reduce errors that would potentially be introduced in translating some of these files. For example, if we're generating a C header file from a list of registers, if we're doing that manually, chances are we're going to make a mistake. And there were occasions where that actually happened.
So Jamsheed, tell us about one of your most challenging projects. Why was it difficult? And what did you do to address the challenge, or what is one thing our audience can take away from the challenges you faced?
Yeah, Josh, I guess one thing that I can point to, I mean, we just talked about early on adopting the one source, single source methodology, at a time when a lot of people weren't aware of it. But the most challenging thing that I have faced has been trying to facilitate a three-way communication between the RTL design, verification, and software teams. And, if we just think about, adopting single source as the HSI methodology, one would automatically think that, oh yeah, okay, maybe that sort of communication automatically, naturally falls out of it, but it actually doesn't. And even back then, there were times that I worked on projects where, for example, communication between RTL design and verification was very minimal. right? And when we think about design and verification, we think, oh yeah, there's a lot of communication between RTL designer and verification team, but that wasn't always the case. And then you think about, okay, the role of software. What role software plays in being able to ship a product in a timely manner? And you automatically think, oh yeah, they definitely have to be involved in the design of the hardware software interface. But back then, that was not true, right? And even today, in many cases, you kind of see the absence of the software team in these discussions.
So just like Dave Burgoon mentioned in his interview, getting the software team involved early in the design process helps ensure their needs are met, which at the end of the day is important for whatever you're building to go out.
Yeah, for sure. I mean, software is definitely the long pole, right, in any design effort, and it's very costly. And we as verification or this RTL design engineers really must do whatever we can to at least reduce the cost, right, of software development.
I know that you're on several standards committees and you work in them, UVM and portable stimulus of note. Could you talk about how that impacts this whole communication mechanism that you're talking about as important for the software and the hardware and the verification teams, how your work on the standards committees help that?
Mm-hmm. Yeah, that's good. That's a good point, Josh. Well, first of all, working on the standards, let's say just the UVM standard, right? It has benefited the verification community immensely because instead of being confronted with a lot of different solutions in the verification arena, now we have a single standard where we actually have to we're able to develop IP reuse. I mean, reuse is because it has become really, really important, and being able to kind of point to a single standard in verification where we can both think of modularization and reuse and vertical reuse, that's very, very important. And then we think of the role that just the UVM standard has played in being able to understand the challenges of, we'll just stick with the hardware software interface, right? And being able to kind of come up with a parallel for that in System C or UVM System C even, right? Today, there is a system, UVM System C, which kind of piggybacked on UVM. And having that solution for the System C environment is just immense. I mean, I think people in the software world can definitely point to the efforts of UVM and the UVM standard. And I'm pretty sure they agree that it's been really instrumental in moving the ball forward for them.
Well, Jamsheed, thanks for the time today. It was great catching up with you.
Yeah, thank you, Josh. Thanks for this lively discussion, and thanks for the time.
Now, let's welcome Rich Weber, CEO and co-founder of Semifore. Rich, you've been involved in many designs, complex, from big and small, because I've known you for a while. Can you share some of the experiences regarding the hardware-software interface of those projects? What went right? What was a challenge? And what did you choose that went well?
Well, thanks, Josh. Yeah, I guess I've been around the block for quite a while. And I remember my very first job out of school was designing a new workstation. And the thing that struck me, certainly with hindsight, is that the very first thing we did is we worked with the Unix kernel team to define what the address map was and how the device worked, all the peripherals and whatever that were in that workstation. And And that was sort of a theme through most of my career. Every project started with, let's have a conversation with the Unix kernel guys or the device driver guy or team. And so all of those projects. And so starting with workstations, supercomputing workstations, actual supercomputers, and then carrier class routers are projects that I worked on. And the teams went from 10 people up to well over 150 people working on a project. And clearly the complexity was going up as the size of the team was going up. But that was a theme throughout, which was talk to the software guys early, figure out what the address map was, design it, and then when you get to the lab, all of a sudden the system actually comes up and you don't have to stress out about waiting for software to be ready, because it's already ready by the time you got to the lab. Now, I can't say that my career was perfect. There's some examples that we didn't do things right. One project at a very large networking company, we were told that the software team was unavailable and that we should just figure out the address map on our own. And so the RTL designers, including myself, took a stab at figuring out what the address map should be. And that turned out to be the largest disaster in my career, where a year after the product was already in the field, the software team finally got to the stage of writing device drivers for certain parts of that design. And we found they couldn't, and we had to respin the design and replace all that equipment already out in the field. So that was an extreme disaster, years of delay, millions of dollars, just because the software team was unavailable. So over the years, best practices that I've, I guess I would say in the hardware software area are, first of all, absolutely have that conversation with your software team on how this device is going to work once it's doing its function, and make sure that conversation is with the device driver folks. I guess another thing that we've done in my career, certainly in the supercomputer days, we prided ourselves that in simulation, we would get to the Unix prompt. And so that was our sort of our criteria for tape out, is if we could just get the simulation to pass all the way to getting a Unix prompt, we felt comfortable that we gotten all the device drivers right, and that the system was solid enough to be worthy of going to the lab. In the networking world, the equivalent is getting a ping to work, basically getting packets back and forth through the whole system and route it and whatever. That was our criteria in simulation to get to ping. And that sort of goes to another aspect of this, is virtual prototyping. So in some sense, we had a virtual prototype of the design, even back in the 1990s when we were just running Verilog and trying to get the Unix prompt up. We had a model of the system. I can't say, I've tried emulation off and on in my career, and sometimes it was successful. Other times it seemed like a lot of make work. But having the experience of having the software do something before taping out the chip was very helpful in rooting out the last few showstopper bugs. And then in most cases, we were ready to, I guess most of the chips were first customer ship. So in other words, the first tape out was good enough that we could actually ship it to the customers. So anyway, that's basically big hardware software interface lessons that I learned in my career.
Rich, that's a good point. Many people have talked about getting the software team on board early, including people in this discussion today. But most of the people that are attending DVCon are rank and file engineers. How do you suggest they go about facilitating that discussion? Because they're not project management.
Yeah, thank you. That's an issue. Certainly for most of my career, I was a rank and file engineer myself. And basically what I ended up doing is I actually developed personal relationships with the kernel team or the device driver team. And fortunately, I was able to do that. I mean, we traveled from site to site, and I went out of my way to actually have, I guess, outside of work time with those people to develop that personal relationship, and certainly that was an important thing. Being able to walk up to somebody, have that personal connection, and be able to have a conversation on how things are going to work. And so, as a frontline engineer, that's what I did. As I actually sought out my software buddies, and had that relationship and those conversations.
Rich, one of the areas that is helping facilitate these conversations is standards. Can you elaborate on how standards help?
Well, thanks for that particular question. First, I want to call out Dave Burgoon for noticing that we've spent a lot of time on standards. And first thing to realize is that standards involve a lot of volunteer work by a lot of different individuals, putting in thousands of hours of time to get to the standards where they are today. One thing I really want to mention is that the standards provide a lot of leverage in the industry, where all of a sudden you can, let's say, come up with an API or something that people can use across the industry. And that saves a lot of time, because without that, everybody is forced to develop their own. And so certainly things like UVM provide a way for the industry to come together and agree on an API, and everybody be able to leverage it. So that's a good example. Another thing is being able to move information from one company to another, or tools to tools, and IP Exact is an example of that. So basically, the standards are sort of an accelerator for the industry. It gets rid of a lot of duplicated work and lets everybody focus on what makes their product special, instead of just what do I have to do that everybody else already does.
Thanks, Rich. It was fun to ask you questions. Your answers were informative. I hope many of our viewers got something out of them. We'll be now moving to the live Q&A session with my guests. Have your questions ready. Before we begin, I wanted to share a short video we've been showing at DVCon. Making an error in hardware-software interface, or HSI, can be dangerous as well as costly.
This is Frank. Frank changed the RTL for one field in one register, and he didn't tell anybody. That caused the software on the chip to stop working, which caused the drone it was controlling to crash into the home of someone who got a bit irritated.
If Frankie had just used CSR compiler from Semifore, we wouldn't have had a meet like this. You see, the software on the chip always runs because CSR compiler is always right. You ain't gonna make a mistake like that again, are you, Frankie? CSR compiler by Semifore. Don't get hurt.